And let's move to the next speaker, that is Wolf von Klitzing. So Wolf is a research group leader in Heraklion, Crete. He's renowned for his experimental achievements on high, extremely bright BEC sources and guided coherent matter waves, including a rapidly spinning condensate at more than 16 times the speed of light. And among his center of interest, we have coherently guided matter waves, interferometry, beams in space, and atom lasers. So welcome, Wolf, and we look forward for your talk.
Thank you very much for a very kind introduction. 16 times the speed of light, maybe not, maybe it's the speed of sound, but
sorry,
yes.
sound, yes.
Having had such a beautiful theoretical talk, yes, I'm going to talk to you about something that's not quite as theoretical and fundamentally beautiful as the previous talk, but I'm going to talk to you about atomtronic matter wave optics, about waveguides, about how to manipulate Bose-Einstein condensates. The main people involved in the paper are these four: Sora Pandey, Hector Mas, and Yorgos Vassilakis and myself. Sorab and Hector have left me for the United States, and Yorgos is now group leader also here in our institute. In the meantime, the group has grown a little bit, and I hope you'll hear from the other people soon. Funding, okay, I have a FED grant and various other sources. Let me come to a little bit of a motivation for atomtronics and guided matter wave optics. Especially seeming that I'm almost the first one to speak about real matter wave optics, at least today. So one of the fascinating things with atoms is the particle wave duality and the interference phenomena that we've also heard about now very much. And one of the most interesting things to measure in matter wave optics is gravity. Why gravity? Atoms fall, gravity has a very large effect on it. And so it can be a very sensitive thing to measure it with it. Or generally, if you want to do matter wave interferometry, you need time to do your experiments. And if you need time, the atoms fall, they fall over long distances, and hence the experiments tend to be very, very large. So the 8-meter tower in Stanford probably by now counts as one of the smaller ones. And experiments go up to 120 meters tall, where they drop a whole Bose-Einstein machine, all 120 meters, apparently without destroying it. But if you want more time, you need to go onto the Vomit Comet, a plane that flies in a parabolic trajectory, something I will never, ever, ever do, or into space. So there's now a lot of interest in space missions, and the EU seems to be going ahead with a gravity mission to measure the famous potato of Earth. Good. So yeah, we're involved in all of these, and it becomes very difficult to do these experiments, obviously, because sampling times become very large. Here you can, in the 8-meter experiment, you can maybe do 1 per minute, one experiment. Here you can do 2 per day, and here it takes 10 years only to launch the experiment, if you're lucky. So it becomes very difficult. So the idea is to do it on Earth. If you want to do it on Earth, you have to compensate the gravity, you have to hold the atoms. So that's one branch of atomtronics. Atomtronics, of course, has also other interests, but that's one version to see it. And the basic idea there is to make circuits where you can guide atoms, where they move, where you can manipulate them, where you can take a stream of atoms, you can then split them into two, maybe combine them with another one, maybe combine them again, probably have a flux gate, a little piece of flux in the middle. I was actually hoping that Michael has some idea of what we can actually put through our rings so that we can see this Harmonic effect in this sort of circuits as well. But this is the idea. So this is what we want it to look like, right? So like a train station. We go in there with our train, which is the atoms, and we can manipulate it, make the trains collide. Okay, there it breaks down a little bit, but okay, that's what we want to do. Reality, unfortunately, looks a little bit different. This is unfortunately what matter wave circuits look like in reality, in practice. We don't have straight tracks. Whenever you lay down a tract, in order to define the path for the atoms, your path is always a little bit warped. There will always be imperfections in the currents. And what we have found more recently, some of us have found, is that even if you make the track perfectly smooth, the crystal structure in the copper itself will make the current meander through the copper. And even if the track is perfectly smooth, the magnetic fields will not. And that causes big trouble, because if you bring the atoms closer to it, they will see this changing potential. And as you travel along the track, as you move them along the track, they will be shaking. Just imagine taking that track in a high speed, and you get the feeling what's going to happen. The atoms are being shaken like hell, and are being thrown out of their ground state, or the transverse modes are going to be mixed, and there's no hope of getting interferometer working like that. Now, some time, a little while ago, in 2004, Chris Foote looked at this in greater detail, and he looked at what happens to this rugosity, to these corrugations, as you move further away from the tracks, from the magnetic guides. And he found some power series, which for long distances, so if I take now K to be the wavelength of this perturbation, so any you want to, it's a spectrum, but any spatial frequency that you take, and Z being the distance as you move away from the track, then there's a beautiful approximation you can do for Kz larger than 1. And that is, it drops exponentially with a correction of square root of Kz. So as you move away very quickly, you get something that's really smooth. Now, it sounds like magic, but it isn't, because you lose the structure itself. Because the very distance between the wires that you chose is what defined you the track. So you have, for example, 2 counter-propagating currents, or even 3. A typical circuit is we have 2 in one direction, 1 in the middle going the other. So then you get a trap that would be above. But as you move further away, you lose the radial confinement. So you have to find some other way to create this. And it's not exactly topology, but it has to be something else, not the shape of the traps. The shape of the tracks cannot be used in order to define the very circuits you're doing, because then you have to have that length scale on which you define your circuits in the tracks. And this in terms means that any imperfection, which will also by definition be on that length scale, will destroy your circuit. So it doesn't work. So what can we do? What other thing can we do? Well, we can use something which we termed time-averaged adiabatic potentials. And they're being created from magnetic fields. So we use rubidium atoms. And they're being used from quasi-static, time-averaging potentials, and adiabatic potentials, stress potentials. And they're separated by the trapping frequency. So I will do a very daring experiment. I've brought you my favorite rubidium atom. I'm going to stop my presentation for a moment, hoping that it will not crash completely. And I will demonstrate to you what these timescales are using my rubidium atom. So here you can see it. So you can see my rubidium atom, right? So normally adiabatic is I move slowly and my atom moves with me, right? So that's adiabatic, nicely, but everything is slow. So then, as I move faster, I come to a point where I hit the resonance frequency. So now, even for very small motion, you can hardly see my finger move on zoom, you get very large oscillations. Then, and that's obviously something to stay away. If your train moves, if you hold that pendulum and your track's on the right frequency, then that will destroy it. But what I can also do is I can move faster. So now if I move very fast. So now I'm really moving very, very fast, but the atom basically stays constant, right? So that's time averaging. So the atom sees the time averaged potential. If you look closely, you see there's a small, if I do it properly, yes, it's a small contribution which makes it increase the potential of the atom, but it stays in place. There's a little micro motion, but it stays in place. And then I can move even faster, move really, really fast. Then this pendulum would invert, and that's then a resonant transition, and the coupling between the two causes the adiabatic potentials. So now let's pray all that we get back to the presentation. Yes, it worked. Good. So that's the thing. So if I look at the time scales now, quickly, yes, at the time scale. So in our experiments, actually we use just about all time scales there are. So we start from experimental repetition, which is of the order of minutes, so 10 to the minus 1 seconds. We do manipulate things. You will see later, we create lenses, moving lenses and so forth. What happens on the time scale of a second. The time averaging is in audio frequencies, about 5 kilohertz. The dressing, that is where we induce resonant spin flips adiabatically, is at 3 megahertz, 10 to the 6. We drive hyperfine transitions as beam splitters, for example, or to manipulate the internal states of the atoms. That's at 6 gigahertz, 10 to the 10. All of the previous ones are all phase locked. They're all linked to a Iridium atom clock to make everything nice and stable. And then, of course, you have detection and optical manipulation at 10 to the 14. Now, dress potentials. To some of you, this will be utterly trivial, but never mind. So this is now a spin 1/2 particle in a magnetic field. So we have a magnetic field increasing here. The energy goes with the increasing magnetic field if it's plus, minus if it's negative, depending on whatever. Then I can shine in a radio frequency magnetic field, which will be resonant at some frequency where the photon energy cup is exactly the distance between the two states. And then what I do is I do a Floquet Hamiltonian, which means just multiplying everything, taking the photon field into account, which then shifts everything. So I get the crossing, I forget about the other states. Since it's coupled, I get a coupling. And so now I have an adiabatic state. So the splitting is the coupling, so I have to re-diagonalize. But now I have a state. So what I see is this here just looks like a trap, right? It goes down, it goes up, and it's some magnetic field, the resonant magnetic field, there's a minimum. Good. So what does that look like in practice? So if I have a quadrupole field, then I know that the field increases in all directions. And I'm ignoring polarization for a moment. But the field increases in all directions. That means it doesn't matter which direction I'm going, the field will increase, my potential decreases, then I hit some minimum and it increases again. Well, that looks just like a bubble, right? So it's like a soap bubble. It's like the soap on a soap bubble. That's where I can trap stuff. And that's an absolutely fascinating object. I mean, also topologically thinking, since years, I just love that. Because you take that bubble, you put a vortex in there, since that's the topic of that previous lecture, you put a vortex line through that. That vortex line has to enter, but it goes through, right? So then I have these, at the top and bottom, I have these vortices sitting, but these are isopotential surfaces. So the vortex could move freely around there. And if I move it to the top, I see, oops, the net vorticity of a bubble is always 0. So it's a fascinating topic the object to work with. Unfortunately, I'm working in Greece, and so they don't pay me to take the space station on a spin and work there and use the space station for a few years. So I have gravity, and gravity just pulls the atoms down, and I end up with a teacup. A teacup is a cigar, is topologically boring. Now, what can we do though? We've seen the time averaging, right? I can very, very easily displace a quadrupole simply by applying a homogeneous potential. A homogeneous field, sorry. A homogeneous field plus a quadrupole field is the same quadrupole field, just somewhere else. If I oscillate that homogeneous field, I can oscillate the bubble. You can see immediately that on the sides, just strictly nothing is happening. It's just tangential. They're just very, very little. The atoms see almost nothing. At the top and bottom, though, you're crossing this harmonic potential. So you're doing this time averaging. If I just time average across two harmonic potentials, then you can see that it has to go through the crossing point of the two. The energy increases. The energy increases in the top and bottom, and ta-da, I have a ring. Right? So now I have a ring. And yeah, I can actually, this ring, I mean, I can, depending on what I do, I can do different rings. For example, here, that's a ring superimposed with a little bit of a figure of 8, or more of a figure of 8. And here I use the Riouffi-Pritchard potential instead. Various things. This is instead of just moving up and down, I go in a circle. Then I get 2 disks, which I can then approach. And if I use multiple radio frequencies, I can even make, or I could make, because I haven't yet, but you can make rings, stacked rings, either on top of each other or inside each other. Inside is a little bit easier. But the most beautiful, important thing is we can do it. So now we can really load atoms into a ring, and this is a real absorption image of atoms at about 30 nanokelvin, about 300,000 atoms at 30 nanokelvin in a 1 millimeter type ring. Now, I can also take different spin states. I'm working rubidium, so I can do F1, F2, whatever, and you can shake a little bit in various forms. So we can make a flat waveguide. We can put atoms on one side, make them propagate. Very important, we can tilt the ring. So if you take the ring, it's horizontal, then it's a nice ring. I can tilt it a little bit, and then gravity is added, and it pulls to one side. So you can do this, you can tilt it. You can increase, I'm not going to get much into that unless someone forces me in the questions. The polarization also matters, the coupling strength matters. So if I don't use, in this case, for the ring, for example, using vertical linear polarization, I can tilt it a little bit, then the coupling is different in different parts, and I can make other single rings, and that's then also state dependent. Upshot being, we can manipulate completely independently the 2 spin states, F1 and F2, F1 -1 and F2 +1. We can move them anywhere in the ring, around, and yeah, good. So, and there's some, I'm not going to talk much about that, but there's a proposal of how to base an interferometer on that by moving these buckets, as we call them, around the ring, and then make them interfere via a microwave beam splitter. Good. Let's stay at the more atomtronic aspect of things now. So first thing is, as I said, we can put the atoms in there, and this is the magic proof of the pudding picture in our field, right? The binomial distribution. So you can see it in the bottom here, nicely the Gaussian distribution superimposed with the very nice BEC distribution. So that's a cut through here, right? Then that's for a concept. So what we take for the experimentalists amongst you, what we do is we first create a BEC in a hybrid dipole trap. So magnetic field plus dipole trap, we make a BEC. Then we create the ring potential and then load the atoms almost losslessly into the ring from the dipole trap. That's because it's technically a lot easier than doing it purely in a magnetic trap. Now, we load into the tilted trap because that matches what the dipole trap almost looks like. And then what we can do is we can just release the tilt and let it flow around the ring, right? So we fill the ring. Okay, one thing. Then what we can also do is we can accelerate. And the acceleration actually is nice the way we do it. We do it with the so-called bang-bang scheme of optimal control theory, which is, to my mind, a little bit the victory of words and a proof that physicists are actually pretty good at public relations at the end, because every crane driver knows how to do that. So you wonder, why? I'll show you. So that, since we've seen that works, so I take my tristate rubidium atom again. So if you want to, so again, we said we can do it adiabatically. We can move the atoms like this, right? But if I want to get it from here to here very quickly, how would I do it? If I just go like that, then, well, that's not going to be good for my interferometer, right? Going slowly is also not an option because that's very large distances. I want to go over a millimeter. If I do that adiabatically, then it will take me best part of the day and it's not going to be there. So what you do actually is you use the fact that if you displace the trap very quickly, it oscillates, right? You just like that. But at the moment after you displace it, you're in a funny state. So this is a harmonic oscillator, right? A harmonic oscillator has the incredible property that its curvature is everywhere in space the same. So the trap confinement is everywhere the same. So the difference between this here and this here is you can either see it as a displaced trap, or you can also think of it as still the harmonic trap being here, but a homogeneous force applied to the atoms, right? There's a homogeneous force now, or acceleration, that acts on all atoms in this direction. Now, if I take this point here, and at the same time that I'm here, I accelerate very quickly out of the picture, then the atoms will not see any in their moving frame, they just stay in the bottom of the trap, in the accelerated frame. So what does that mean? That means, and that's where the crane driver comes into, it's actually very easy. You just do this, oops, right? Here, whoop. I can just move the ball over here, very simple. So what have I done? I've moved the point over here, I accelerate until I find my target velocity, constant acceleration, right? Target velocity, then I'm reversing the acceleration, plop, until I'm standstill, and the moment I stand, I just move my point back over the top. So, I mean, I've seen that with the Acropolis, when they renovated the Acropolis, and they moved these absolutely invaluable arcane figures from the Acropolis up on the Acropolis down to the museum. That's what they did. They went, they accelerated, they stopped, and plop, they stopped. So it's a good trick. Now that you know that, it's a good party trick where you can win against almost anybody by moving this, by moving something without shaking it. Well,
So,
okay.
Wolf, 10 minutes.
10 minutes, oh God. That is very, very poor timing, I must say. And that is. Okay, good. So that's the bang bang scheme of acceleration. It really works. So that's where the movies don't work. So I can really, really move them around. We can accelerate them, and that's just saying the same like I did before. And the fascinating thing is it really works. So here you can see that's a linear motion. After acceleration, we just keep the trap rotating around, and there's minimal residual oscillation. That's because we just didn't time it very well. But there's, if you look at this, this is milliradians oscillation over duration of 15 seconds. And then I can look around and I see that after 5 seconds, which for BSC is eternity in these traps, I still have a BSC there, and I cannot see any heating. The heating from the motion is 0. Whether I keep it steady or move it, I will get the same sort of loss and the same sort of heating. And the amazing thing is, if I look at the superfluid velocity, the velocity of light of the atoms, then I find it's Mach 17, right? So it's 17 times the velocity of sound. And at first, of course, it sounds impossible because it should explode. But it only explodes if there is any roughness. You need something to hit it in order to explode it. And so that just proves that the waves are perfectly smooth. And why is that? Well, that's what we learned from Chris Foote. And so if I look at the experiment, this is where it happens, then the distance here between the coil and the atoms is about 5 centimeters, 50 millimeters. The BAC, the ring itself is 0.5 millimeters. So the wavelength that I have to take into account is about 500 micrometer. And then if I calculate the K times Z, it's about 630. So it gets attenuated to 10 to the minus 275, the roughness in the wires. So clearly, I don't think there's any formula that works at 10 to the minus 275 precision. But what it just means is it's just not there. And that's why we can go to Mach 17, because there is no roughness. It's not, there's no magic, there's just no roughness. And that's again, because the potentials we create are not based on some structure that creates the potential, but it's sort of topology. It's not exactly topology, but anyway. So we can also let it expand in the ring. And then we get this here, a very nice round ring. And I'm rushing a little bit through. The angular momentum is absolutely silly. It's 40,000 h-bar per atom. So it would be very deep into the in the Landau regime, in the quantum Hall regime. But we are not harmonic, we're not perfectly harmonic, so we can't see that. The roughness, again, then I can still have deformations because my system allows me to have up to the second radial harmonic, and that's what we see. So if you look here, you can see there's a little bit more atoms here and here, a little bit less than there. That corresponds to about 200 nanokelvin. In the moving, if I make the condensate move, and that's one point which I find quite fascinating. If you make it move, then in the moving frame, the atoms time average over this little tilt in the potential, and I get an extremely smooth potential, extremely flat potential in the time average. So it's of the order of 100 picokelvin. We can go down to 50 picokelvin now quite easily. And that's fascinating because now I have a system where I have a waveguide, which is completely smooth. I can move the atoms around. It's flat to 100 to a few picokelvin flatness. And because I have complete control over the system, because I know exactly the angular velocity of the atoms, I can have co-moving barriers. And so I can make lenses that co-move. Okay, I'm going to jump this. This is what Gretchen Campbell also talked about. So what I can do is, I can have the tilt, delta is the tilt that I'm putting on there in a co-moving potential. So here I'm moving, it's basically a trap that moves along the ring. Then I ramp that off, I let it expand. And here, this here is basically a thin lens. I just tilt the ring for a moment, and that's a parabolic potential switch on, which is mathematically completely equivalent to a thin lens in optics. So I can have the atoms. So now on the left-hand side, you see free expansion. On the right one, with this lens timed nicely. And so I can use that lens to collimate the beam. And the
5
result
minutes.
is then, sorry, 3 minutes.
5 minutes.
I was carried away with the fun part. So, okay, so now if I look at the strength of the tilt, that's basically the focal length of that lens, then I can tune that and I can focus my system, right? Just like in optics. It's just like, it's a complete equivalence. And I really love that. And we're working on that theoretically also now. Matterwave optics is, the wave is then the particle, and the lens is the electromagnetic fields. And mathematically, actually, down to some very deep details, the equations are the same, they're identical. So here I can now focus the lens, and then I can look at what happens there. I can look at the focus. So here that's the bit where I focus. So these are nice pictures in the ring, and I can see above it focuses, not terribly interesting. But now I take the case, I release the condensate or the thermal cloud, blue condensate, red thermal cloud, into the ring, and it expands, right? No surprise there, either because of thermal energy or because of the chemical potential. But I can also switch on my lens. And now I switch on the lens for a moment, the thin lens, such that I try to collimate the beam. And it works magically. So what you can see here now, the solid, the dashed line is, as I said, free expansion, and the blue line is the collimated thing. And what you see is the temperature drops by a factor, the chemical potential, so measured in Kelvin, drops by almost a factor of 50. So we can really manipulate the atoms. We can really take out this energy and reach incredibly low temperatures. This is 800 picokelvin. And this is particularly impressive because, I mean, these temperatures have been reached before. But this is like in the 10-meter drop tower of Kasevich. They have managed to collimate a beam down to these temperatures. these kind of chemical potential temperatures. But here it happens in a half a millimeter ring, in a tiny, weeny little ring. Good. So I didn't manage to rush to the end though. So we have made a Matterwave accelerator ring using this bang scheme of optimal control theory. We've had a lossless hypersonic flow of BSCs. We've created ultra high angular momentum. The latest thing is that we're also looking at giant vortices and these things. We've made some atomtronic optics, delta K cooling. We have also state-dependent control. And we're now looking into we have one limit where it's completely lossless. On the magnetic circuits, we have the really, really high loss range. So it would be nice to scan to introduce artificial roughness and scan the regime in between and figure out what are the limiting factors, how does it work? And with that, a little bit rushed, thank you very much.
Thank you very much, Wolf. And so there are a few questions already in the chat. You can have a look at them.
Look at them.
Do you have access? Yes.
I have, I think. So are these curvy rail tracks you showed? Where are these? I think in India. I think they were in India, but I'm not entirely certain. It's not. It's just a picture. Not in Greece, if that was the question. Carsten Henkel asked, an atom with its magnetic moment going once around the ring must have its spin adiabatically following along some path that closes onto itself. How would these see the associated geometric phases? That is really something I was hoping to understand better from our previous lecture. So first there's a motional phase, right? That's just the standard flux quantization, which, by the way, in our case is difficult to show because these rings are gigantic, and the energy scale that we're talking about is about 1 over half a day or an hour, something of that scale. We can also go smaller, but for these rings, there's nothing of that left over. So it's just actually the flux quantization, which is associated to the winding of the phase along there. I have not found a way how to punch something through there that would give us a true geometric phase. So yeah, I turn the question to the audience. Do you have control over the angular momentum? Yes, actually very, very precise control, because this acceleration, I haven't actually elaborated this, but we're programming essentially sound cards, and the frequencies are locked to atomic clocks. So the acceleration is extremely precise. And so we have very, very good control over the high angular momentum. We cannot make low angular momentum numbers just simply because the acceleration is just nothing, right? I mean, it doesn't live for an hour. So right now, with the way we're doing it right now, we do not have the time to see these things. We're working on that. It's going to come, but yeah. During the flow, due to the friction between atoms, is there some heating expended or not? Since all the atoms are moving together, no, there is no friction between the atoms. So in a ring, it's a little bit, yeah, in a ring anyway, there's a rotational symmetry, so there's nothing happening. Yeah, so I don't expect any friction from that. How do you check if the atoms in the ring remain a BC after acceleration? By the binomial distribution. So I've shown to you that there's a Gaussian background in the radial direction in this case. There's a radial distribution. We look at the radial distribution as a Gaussian with a typical parabolic shape in between. One thing where it becomes really difficult is what you see here. In this one here, you see an expanding, where you can see the numbers. if you expand the condensate back into itself, things become much more complicated because you have counter-propagating flux of atoms. And so as you expand it, the momentum stays. So it's sort of a spiral BEC. And there, yeah, that's a bit more tricky. So there you can still see it's a BEC because it has the, you can actually see in the larger expansion times, you can see there's a black line in the middle and some fuzzy stuff around it. This fuzzy stuff is the thermal atoms. The black line is the BEC. But
okay,
as it goes back to itself, it becomes more difficult.
Okay, sorry, I thought you were finished. You had asked. There is a question from Luigi now.
Luigi?
Yes. No, I mean, quick question. So, do you think you can split the condensate and make them collide?
Absolutely. Yes, that's something we want to do.
At that speed?
Yes.
So you make an LHC.
Absolutely, we can make two condensates, for example. So if you have if you take the radio frequency, either if you take the linear radio frequency tilted slightly, then you can see the projection on the magnetic field on this side and this side is different from that side and that side. So the coupling strength is different. That means the potential is different. That means you create two traps, or you can just shake it in figure of 8. So you make two traps, and then it's a bit more complicated, but we can do that because we have full control over all the fields. If you make it slightly circular, you can move these two troughs towards each other, and so you can accelerate them towards each other, you can make them collide. And I'm actually quite excited by that because we can access kinetic energies that are very difficult to access in any other way. So we can have them collided very, very low velocities, and that would be interesting.
Thanks.
Okay, so there is the last question on a closed subject. How do you plan to realize an interferometer, and what is the main experimental challenge
in doing so? Partially, I've always been scared of starting, but I think so. One thing is you have to work at very low atom numbers because of chemical interaction, or probably it can also work with thermal atoms. So, so there are two different ways to do it. One is you load the atoms on one side of the ring. You use a microwave pulse to couple the F2 minus 1, so plus 1 minus 1 and 1 minus 1 condensates, which have under certain conditions, under certain field conditions, exactly the same confinement. You couple them and then you manipulate them separately and just carry them in a bucket around the ring. Alternatively, you can just give them, just put a standard Bragg, okay, that was the F1M1. So to do a microwave pulse, then they go the same way, but the atoms do a turn, but the state does the half terms, and then you get the two. This is not what I wanted to show to you. And I thought I had another one, but no. But the other method is with Bragg pulses. Bragg pulses, and then some lenses in order to refocus them. So that's another little advertisement. In case students want to come here, this is what it looks like here in March.
Okay, then
I booked the flight.
Yes, it's a nice one,
beautiful.
right? So PhD students, postdocs, that's where you spend all your time. Please apply now. We have 3 positions open.
Okay, then thank you very much, Wolf, for this very nice talk with animation.
Thank you.
And okay, then see you soon. There will be a couple of extra questions that will be sent to you.
Okay, great. Thank you.